So welcome back, everybody. The topic today is to repeat some of the essential elements of neural networks. And we are also going to look at how we can use a library like TensorFlow, which was released by Google back in 2015. And this is similar to a library which was released by Facebook, which is called PyTorch. There are many, many other such libraries. And you should feel free to use the one which you think you're most familiar with and which you think is the most flexible one for your needs. Now, TensorFlow has become one of the more widely spread libraries, and it has an API which is called Keras, which allows for an easy way of setting up deep neural networks. And these can be convolutional neural networks, so they can be recurrent neural networks, or any of the other advanced methods. So tools like your library, like scikit-learn, which we have been using till now, are libraries which have normally just a simple neural network, like the feed-forward neural network, which we discussed last week and the week before. And it does not have the same range of methods in deep learning which typically TensorFlow has. So TensorFlow can also be run on Google's Colab. And normally I recommend using Google Colab because sometimes there can be some problems with installing TensorFlow. There may be some conflicts with Python versions. And if you have the newest Apple laptops with the M1 processor, there have been some problems with having TensorFlow to run properly with the M1 processor because many of the drivers and the libraries have not been updated to run on the new processor. So if you have a brand new Apple with an M1 processor, you may have some smaller problems. And Google's Colab, which we are going to look at a little bit later today, allows you also to access GPUs and CPUs, so you can run your codes pretty fast. There are many people using them, so you may end up in the pipeline and waiting for your job to run. But in general, if you don't want to install TensorFlow on your laptops, I mean, you can use the web interface from Google's Colab, which is very nicely set up and runs smoothly. Okay, so as I said, the topic today is to give you a quick introduction to TensorFlow. I also wanted to remind you of the things which we did last week. And then we're going to say something about the pros and cons of neural networks. And then when we're done with that, the topic which we will put more emphasis on is solving differential equations with neural networks. And that's becoming a very important field of applications of neural networks. And that is mainly due to the universal approximation theorem, which says that you can actually approximate with at least one hidden layer any nonlinear function, complex function, with just one hidden layer. And this is something which is very, very promising for systems of like linear equations. So if some of you is going to study, let's say, turbulence using Navier-Stokes equations, this is a field where people have started to investigate the role of neural networks and deep learning methods in order to solve high dimensional and complex sets of differential equations. However, before we move on, I wanted to bring you a little bit back to where we were last week, because we had a topic which we didn't finish properly. And if we go back to the slides which we had last week, so I'm just going to bring up the plain HTML here. There was a system which we didn't explore fully. And that is a very simple test of neural networks. And the test then is actually to be able to reproduce gates, which are called the XOR, OR, and AND gates. So let me briefly explain to you why these are interesting test cases of neural networks. The interesting thing here is that you can use these cases as examples of where a single perceptron model, I mean, without one hidden layer, actually fails in reproducing the output from an XOR gate. It reproduces correctly the OR gate and the AND gate, and you will now see quickly why it reproduces two of these gates, but not the XOR gate. So let's take a quick look at the things on the whiteboard here. Let me just stop that one, and then we move on quickly to the whiteboard, because this is one of the cases which you will find in many, many textbooks about the output from a neural network. And the thing is that the XOR gate has been used as one of the demonstrations for where what we normally call a single perceptron model, which you can show can fit mathematically an equation or a problem set which is linear in the input variables. So let's take a quick look at these examples and show then how actually a neural network would reproduce properly the XOR gate when you have at least one hidden layer. So we're not going to prove it mathematically, but we're going to demonstrate it numerically. So these are some interesting cases in the applications of these systems. So these are three classical gates. So it's the OR, and then we have the AND gates. And what you have then is an input signal, and then you have an output signal. So you would have, you could have, if you are looking at an OR gate, the typical input could be a bit 0 and a bit 0 here, and that would output 0. If you make a table then, what you would have, you can have a table like this. You have an x1, an x2. So this is the y value. This is the x1, and this is the x2 here. And then you have the final output. And this is a case which you can easily set up when you want to run the calculations. And the design matrix is very simple to set up when you actually have the design matrix immediately. So if you have a 0 and 0, what you get then is 0's output. If you have 0 and 1, it gives either 0 or 1, that actually gives the highest value. You can have 1, 0, that gives 1, and then you can have 1, 1, and this is 1 here. So this is a typical example of a so-called OR gate, which is one of these, many of these popular gates which you set up in electronics. You can have the AND gate. So this is the example of the OR gate. You can set up an AND gate. And in that case, what we would have is the following set of inputs and outputs. The inputs and the outputs are exactly the same. And you see now that if you want to train a neural network, your design matrix would simply contain 2 columns and 4 rows. So it would be a 4x2 matrix with x1 and x2 being the features and taking just 2 possible values. So if we take the AND gate, this is an x1, an x2, and a y here. And then you have, if we now look at the input here, the input is exactly the same. So you would have 0, 0, 0, 1, 1, 0, 1, 1. And that gives us output 0 here, and 0, 0, and 1. And finally, we have the XOR gate, which has the following inputs, exactly the same as before. So I have a 0, 0, 0, 1, 1, 0, 1, 1. And then the XOR gate has 0 here, obviously, 1 here, 1 here, and 0 here. Now, the thing which you can see almost immediately from these data sets, if you now make a plot. So suppose we take the AND gate and we make a plot of the results for y in term as a function of x1 and x2. So we have an x1 here, and then we have 0 and 1, 0 and 1. Now, if we now want to reproduce this system here, if we now look at the outputs, so we know that when we have 0 and 0, then we have an output here. And then if we have a 0 and 1, that means that we are here, we have an 0. So I'm just going to mark the filled circles. These are the zeros. So this is y equal to 0. If I now look at the 1, 0, then I have the same result. So this is a 0. And then I have a 1 here. And what you see now is if you want to fit a model which simply says that I want to separate the two outputs, you see now that you can actually make a straight line in between here. So it means that you can fit a linear model, and then you could say that the results below this specific straight line are 0, and the results above have to be equal to 1. So this is a case where actually you can show mathematically that you can fit a standard linear regression model, or since these are discrete variables, you could fit a logistic regression model. So either one of them is okay. You would simply say that I have found a line which separates the two types of outputs. And then, depending on whether you say the value is below a certain value, it's 0, and whether it's above, then it's equal to 1. If you plot the OR gate, you will see the same kind of pattern, except then you will have 3 observations which are 1, and just 1 observation which is 0. You can still fit what is normally called a single perceptron model. So a single perceptron model has an activation function here, an f of x, and x is now a vector which contains x1 and x2. And then there is a bias here, which could be the intercept, and then there's an output. So it means that your function y here is given by some f of x, where x is now a vector which contains x1 and x2 plus a b here. So you could do that with a logistic regression model, or you could just do that with a plain linear regression. Or you can actually set up a feed-forward neural network with just one node, and that will still do the job. And you can actually show that. It's not that difficult to see that this kind of model here, which is called a single perceptron model, actually does the job for you. However, when we now want to look at this XOR gate, if we make a plot of that one, you will fail with this model, as you will fail with you trying to apply logistic regression or trying to apply a standard linear regression fit. Because if you now look at the outputs, and if we make a similar drawing again, so we would have x1 on the x-axis and x2 on the y-axis, and we have the two possible input values, bit 1 and bit 0. Now, if you look a little bit closer here, we would have a 0 here. But then when it's 1 and 1, we would have a 0 here. And then we have an open circle here for 1, and we have an open circle here. And now you see that fitting a straight line, which goes into this region, or splits the two outputs, becomes very difficult. So we could, if we have a line which goes here, you see that that would fail because we would not be able to separate the ones and the zeros. Or if we make a line which goes here, just to give you some examples, you see again that this is a line which does not fit properly. So this is a case where a standard neural network with one hidden layer and just two inputs and two hidden nodes does the job. So the input layer here is now given, if we now want to repeat a little bit of the basic details of a feed-forward neural network. So you would have an X1 and an X2 here. These are the inputs. So they go into the input layer. And then we would set up a hidden layer. And in this case, it suffices actually to have two hidden nodes. And we would have this one. So we would have weights W11. There will be a weight W12. There will be a hidden layer H1 and a hidden layer node H2. This would have a bias B2, and there will be a bias into this one, which will be a B1. And they conspire to produce an output, which is our Y. and this y can be either 0 or 1. So typically what you would have to say is that in this case, you're not going to produce exactly 0 and 1, but you're going to produce a threshold value, and that threshold value could be something like 0.5. And then you would say that if the output is less than 0.5, you would then say that, okay, y is equal to 0. If it's above 0.5, you would say it's equal to 1. So in this particular case, H1 and H2 conspire to give a final output. So you would have a new weight here. So now we're going to put some labels on it. 2,1 and W22 here. So this would be the labels for the hidden layer, H and H here. So we will have 4 variables plus the 2 biases. That gives us now 6 variables to determine. And then we would have a new weight here, which will be the weights from 2 here and the weights from 1, which conspire to give a final output. And these would be the weights which now correspond to the output layer. So this is what we called the output layer. And this specific node has also one bias, which we can set off as a variable. So in total, this network will have something like 9 variables to be fine-tuned by the neural network. So there will be a bias as well, which we would add here, a B of O, to indicate that this is the output layer. And then clearly we would compare the outputs with the targets. So this is the one of these kind of what we might call classical cases, where you can show that a neural network with one hidden layer is able to reproduce this XOR gate. Whereas if you take just a simple perceptron model, which has no hidden layer, you can reproduce a linear fit, but you cannot reproduce the more complex output, which you get from an XOR gate. Any questions so far? So what we're going to do now is simply to look at some of the Jupyter notebooks and run these cases. So let's just bring up the notebooks here. Let me do that. And it should be this one. Now it's the other one. So this is something which is contained into the lecture notes from last week, because we didn't finish the whole material in time. So let me just scroll down a little bit till we get to this example with the different gates. So the first part here contains us building a neural network for the MNIST dataset, which we discussed both using our own code and also the scikit implementation. And let's just scroll down a little bit here and look at the examples with these different gates here. So you will find the same material which I went through on the whiteboard here listed here. So these are the outputs and the inputs for the OR gate. You would have the similar one for the AND gate, and finally the same for the XOR gate. Now, this is a case which is very easy to set up, and it's actually it's very useful to actually look at it, because you have a simple design matrix, and you could even try linear regression here if you want to. And you could try to just use this as your input. You could try to fit a first order polynomial. You could even be more ambitious. You could fit higher order polynomials. And in this case here, the outputs are simply given by these vectors with 0, 1, 1, 0, 0, 0, 1, and then the finally one for the OR gate here. So you can set up a single network. So you could have this is a simple test code, which does simply the feed forward part. And it's very useful when you want to convince yourself about your neural network code. And if you do a feed forward pass for these simple examples, you could then have a sigmoid as an activation function. You would set up the hidden weights. And in this particular case, you would just have 2 hidden nodes. You have a sigmoid as an activation function. You return a probability from the output, which is given by the sigmoid again. And then you would typically say that, okay, if it's below 0.5, then I put the output equal to 0. And if it's above 0.5, I put the output to 1. And this is then the prediction you would make. The design matrix is very easy to set up, as I said, and the outputs are now simply given by these numbers which you see here. And then you can simply run it. You would have your input features, which is just this X, the design matrix. And then you have hidden neurons, the categories which you have are 2, 0 and 1. And then you have 2 features. And then you can set up the hidden weights, the hidden bias, and produce the final outputs here. So this is just a feed-forward stage without any training. So there's no back propagation. And the prediction here is just a set of zeros, which is not very impressive. So that means that in this specific case, we just predict that all the outputs should be 0. Now, you can test your own feed-forward neural network, or you can simply run it using scikit-learn. And to run it with scikit-learn is again extremely simple. You would simply set up your design matrix and then the outputs which you want to target with your network. You give it the number of hidden neurons, the categories, and the number of features. You can now be a little bit more ambitious, and you can try to set up the different learning rates. You can set up the hyperparameters lambda, and then you can simply call the MLP classifier. The MLP stands for multi-layer perceptron. So that has one hidden layer at least. You will feed in the number of hidden neurons. I use the logistic function as an activation function in both cases. I have my hyperparameters, and then I simply make the plot. And when you now test the results, what you would see now is that for some of the results, and this is where you have to decide whether this is below 0.5 or above 0.5. So when it's 0.5, this is actually the accuracy score on the data. This is what is given as an output. So you can have 0.75. You would then say that 0.75 is equal to 1. 0.75 again, 0.5 and below is equal to 0. And you will see now again an accuracy on the score data, which is 1. So when you now plot it, you will get something like this. So you would have a domain here where you actually reproduce correctly the XOR gate. So this is our XOR gate. And you would then say that when you have an accuracy score of 1, that is when you have classified correctly the outputs. So this is a very simple example where you can train a neural network. It's very easy to follow. And it's a useful test of if you want to develop your own code for neural network. So the things which we discussed last week with setting up a neural network is something which you can actually test here easily. Now, the thing I wanted to do now is actually to set up the usage of TensorFlow and Keras. So Keras is an API which makes life a little bit easier. You can program everything using TensorFlow, but sometimes that introduces more layers of complications. So building a neural network or convolution neural network or any of these neural networks using TensorFlow is something which makes, and Keras is something which makes life much, much easier. So the examples which we have here, just to show you how you would typically install it. You can install it with Conda if you're using Anaconda, or you can just install it on your laptops. The problems you may experience sometimes is that there may be Python distributions which don't collaborate well with the latest version of TensorFlow. So sometimes it can be useful to just run everything through Anaconda. When you use Keras, this is something which normally makes life a lot easier. And I would normally recommend using that one in the beginning here, unless you want to move into TensorFlow itself, which in a way gives you kind of Python-like programming interface, like PyTorch is also doing. And there you can write code which is rather similar to the way you would use a library like NumPy or Pandas. But Keras then becomes a kind of API or kind of interface, which allows you to set up a neural network in very few steps. So what I have here is the data set which we produced for the MNIST data case. So in this case, I didn't run it because on my laptop, which is an Mac with an M1 processor, TensorFlow is still a little bit, how to say, if I don't run Anaconda, it still creates some problems if I run on my Mac here. So what I'm going to do now is to show you the basic commands, and then we're going to look at how you can run it on Google Colab. So the what you would need to import then are things like, let me just change a little bit the fonts here, so things are a little bit easier to look at. So you would need to include, when you use Keras, which is kind of lowest level of pain for getting started with TensorFlow without having to teach yourself too much about TensorFlow. You would have to include the input layers. You need to include the type of model. So this will be a sequential model because this is a feed-forward neural network. So you add layers sequentially. So you have to specify that. We want to have dense layers. You have to import the optimizers. So this could be ADA-grad, it could be a standard gradient descent, a stochastic gradient descent, it could be an RMS prop gradient descent, and so on. You need to include what kind of regularization you want to apply. And then finally, this categorical here stands for the type of output you want to produce. So in this MNIST data case we looked at last time, what we have is a data set which contains 10 images. And that means that we have what we call 10 categories or 10 classes. The thing which is nice with TensorFlow and many of these other libraries is that the functionality which you have in scikit-learn, like this train test split, and many of the other ways of setting up the input data. So if you're using, for instance, a data set which has been tailored to run with scikit-learn, like the Wisconsin breast cancer data set or this MNIST data set, you can reuse everything which you used with scikit-learn, like the input design matrix, the features which are looking after, and so on. So all the kind of all the functionality which you have seen in scikit-learn can be transferred to TensorFlow. So that makes it easy to interface these different libraries. So you see here, typically, the statement I have here is from scikit-learn. I include this train test split. It's actually easy to make your own function for the train test split, but I'm a little bit lazy here, so I've been using the functionality. And what I'm doing now here is to set up my own neural network with Keras. And I define the number of epochs for the stochastic gradient descent, the batch sizes, the neurons in the first layer, the neurons in the second layer, the categories, which are 10, because I have 10 numbers. I specify the learning rates in a log scale from 10 to the -5 to 10 to the 1. And then similarly, I have my regularization parameter, and I'm going to use an L2 regularization. So you can see now that this function, which I created now, simply defines I have a sequential model. I add, so this will be a Keras TensorFlow command, a dense layer with 100 neurons. I have activation function sigmoid. This is something you can change. I have a regularization function of the L2 type. I add the second layer, and then I have the final layer, which is now my output layer. I specify the optimizer, which is now a stochastic gradient descent, and that takes in as input a learning rate, which is this array eta, which we defined here, because we are going to have a loop over the eta values. As you can see down here, so this is my neural network. I initialize everything, and then I run over the learning rates, and I run over the hyperparameter lambda, and I'm going to do a kind of grid search to find the optimal accuracy here. And you see now that my metrics here is given by the standard accuracy, which simply calculates the number of correctly classified events. And the optimizer is my stochastic gradient descent, and the output probability is now given by my standard softmax function, as you can see here. And that feeds in to the cost function or loss function, which is now the cross entropy. And this is essentially the way you would use Keras. And here I'm simply calling that function and running over the different parameters here. Now, and then at the end, I would simply plot this using Seaborn, so I get a nice color map for everything here. So I'm going to show you now the way you would use it when you implement Google's Colab. So let me just bring that up. So I should have my screen. So here we are. So with the results here, when I use TensorFlow, so this is typically the way the interface looks like. And I just need to show you the results. So this is the pre-collection here. This is the output of the data sets which we're using for training and testing. And then the function itself, actually one of the things you will see now from the output is that a dense layer with or deep learning model with 2 hidden layers actually gives a result which is a little bit below the results which we had when we used scikit-learn with 1 hidden layer. So the number of hidden layers becomes a parameter in your architecture. So you can see here for the training data, I have a set of results which give an almost perfect accuracy with a learning rate which goes from 10 to the -4 to 10 to the -3, where we have typically training reproductions of the accuracy, which are close to 100%. And then in my test accuracy, I have a region here where I'm getting to 98%. And this would be for a learning rate, which is roughly 10 to the -3. And it would have a regularization parameter, which is something like, a learning rate of 10 to the -2, and a hyperparameter lambda, which spans from 10 to the -5 up to roughly 10 to the -3. And the domain here is actually a little bit smaller than the one which I got with 1 hidden layer using scikit-learn's multi-layer perceptron classifier. So this is something you need to play around a little bit with. So one of the parameters which you, in a way, have to deal with is what defines the architecture of your network, and that is the number of hidden nodes, the number of hidden layers. Clearly, the kind of optimizer you're using may play a certain role, and also the type of activation function which you end up using. So these are all kind of parameters which are parts of the architecture and the hyperparameters which you would end up dealing with when you're setting up a neural network. So this is just to show you how you can use Google Colab. So if you punch in Google Colab in your net browser, you can log in with your Google account or just be a guest. And then you will simply upload your Jupyter notebook, and then you will be able to run it on a mix of GPUs and CPUs. And then you can play around with the different architectures. And my advice is simply just try to test it out and see what you get. And when you're setting up neural networks, I mean, there is no kind of predefined architecture which does the job for you. So what we are going to do now with the end of this lecture and a little bit into the beginning of the next lecture, we are going to look at some pros and cons of neural networks, some of the pitfalls, and some of the kind of small tricks of the trade, which you can think of when you're setting up your neural network. The kind of overarching view you should try to keep is that with the universal approximation theorem, you have the possibility to approximate a continuous function with or the data you want to classify. If you're looking at a classification problem, you can approximate these to a given precision with one hidden layer. It doesn't say anything about how many hidden layers you need and how many nodes there are. It doesn't say, the theorem doesn't say anything about the kind of stochastic gradient optimization you want to use, or just a gradient optimization method. It doesn't say anything about the type of activation function. So these become parameters which you need to tune, functions you need to try out before you reach an accuracy which you are satisfied with. So let me switch a little bit from this Google Colab. And if you have any questions, please feel free to ask questions now before I go back to the pros and cons and tricks of the trade with neural networks and deep learning methods. Any questions so far? Is everything okay? Okay, so what I'm going to do now is just to go back to the slides here, and we're going to look at some of the tricks of the trade and pros and cons of neural networks. So let's just go back here a little bit to the material for this week, which is also about solving differential equations. And let's take a quick look at some of the basic things with neural networks, the pros and cons and the tricks of the trade. So one of the things you may ask yourself is, how do I find the optimal parameters? So we've been talking about the learning rate. We've been talking about the hyper parameter, which we use when we have a regularization term, which often tends to reduce the bias and the variance in the data we are trying to fit. So the kind of questions you may ask now, since there are so many parameters and functions and functionalities to try out, which one should I use first? So the one of the parameters to which the neural network is most sensitive is actually the learning rate. So what many people will typically do then is to actually tune the learning rates first. So you can use things like a grid search. You can do a randomized search. Scikit-learn, for instance, has a very efficient function for doing a grid search of the optimal learning rate and the optimal regularization parameter. There's also dedicated tools. There's one which is called Oscar, and I invite you to take a look at it, which allows you to implement pretty complex algorithms to help you find a good set of hyperparameters quickly. So the basic message is that the two hyperparameters to which the results are most sensitive when you're setting up a feed-forward neural network are actually the learning rate and the regularization parameter. The other thing, for many problems, we normally recommend to just start with one or two hidden layers. And for many of these problems, this will actually work pretty fine. So for the MNIST data set, as you saw, you can actually reach an accuracy of 98% or even more perhaps for this kind of blurred and numbers which were just defined by 64 pixels. The human accuracy here is also roughly 98%. So the kind of neural network which we trained last week with the scikit-learn and one hidden layer and 50 nodes gave us an accuracy which corresponds to human accuracy. So you would typically always start with one hidden layer and a given number of hidden nodes. And then for more complex problems, you can gradually ramp up the number of hidden layers until you start overfitting the training set. And this is something you will see very quickly. Very complex tasks, such as large image classification or speech recognition, they typically require networks with dozens of layers, and they need a huge amount of training data. This is also one of the things against neural networks and deep learning methods, is that they rely on lots of labeled data. So the more training data you feed into the network, the better it does a job. However, that means that it becomes pretty heavy, seen from the number of CPU cycles which you need in order to reproduce the data. So there is always a balance here. Clearly, if you can fit something to perfection, but you're going to run for weeks, you should, or you may consider using simpler methods. And sometimes in typical regression problems where you're fitting a function, the different classes of linear regression methods, whether these are standard linear regression methods or kernel regression methods with some smarter basis sets, they often do a better job. Then the thing which we discussed last week in more detail when we looked at the mathematics of neural networks, that was about the activation function. So this is also a big issue. It is in one way or the other one feels that neural networks becomes a kind of tuning different functions, different parameters till you get the kind of accuracy you're looking after. So the backpropagation algorithm, which we discussed, it uses the gradient descent. And since we do this gradient descent updating of the weights and the biases, which are our parameters, some of the activation functions, like we saw the sigmoid function, results in this problem with vanishing gradients. In other cases, we can actually have gradients which grow bigger and bigger, and the results leads to another problem, which is called exploding gradients. Now, one of the ways to avoid that is a kind of ad hoc method, which is called gradient clipping. So you simply just clip off the gradient. If you reach a certain value, you say that, okay, this is too big. Now I just bring it back to a smaller value. So in a certain sense, I mean, if you want to be a kind of purist, I mean, this is a little bit like cheating. But there are many such small tricks of the trade which are implemented in the setup of neural networks. So the activation function which you should use is something which also plays a certain role. So the as we discussed last week, the logistic function is actually one of the functions which cause this problem of vanishing gradients in the training part. And there is a very interesting paper by Glorot and Joshua Benjo. So Benjo is one of the co-authors of that textbook on deep learning, which I've been recommending. And they found that the problems with the popular logistic sigmoid function, which was the function people used because that was the one which mimicked the way you think neurons fire a signal. And they found that also the weight initialization technique that was most popular at that time, you would have some random initialization using a normal distribution with a mean of 0 and a standard deviation of 1. They show that this activation function initialization, the variance of the outputs of each layer could be actually greater than the variance of its inputs. And when you went forward in the network, then that led to gradients which would slowly just start disappearing. And that is simply because the arguments to the sigmoid function started to become a little bit too large. So I'm not going to go through, you can read the slides here, I'm not going to go through everything, but there's a very good discussion in this paper by Glorot and Benjo from 2010. And we have this other family of function, which we discussed last time, which is this ReLU function. That's one of the activation functions. We have this leaky ReLU function, which has a smaller value for the negative input values, Z. Then we have the exponential linear unit, which is also used a lot, where we have an exponential -1 for Z less than 0, and then it just is equal to Z for Z larger than 0. So which activation function should we use? In general, it seems that this ReLU activation function is better than the leaky ReLU, which is often better than the standard ReLU function. And in some other cases, however, you might find that the tanh and the logistic function actually do a pretty good job. So these become, in a way, parameters in your theory. Also, in many cases, people actually use the ReLU function in a hidden layer. And it's one of the reasons for that, it's a pretty fast to compute because you just output the value z, and the gradient or the derivative is extremely simple. It's just a constant, it's equal to 1. So there is always also this balance between the number of cycles you want to spend in the calculations and the accuracy of your results. And for classification problems, when you look at the output layers, it's typically the softmax function, which is the most common choice. And for regression tasks, if you want to fit a function, you normally never have an activation function in the output layer. You just output the result. And that's the one you want to compare with the data which you have. There are many other things here. The renormalizations, the type of stochastic gradient descent, they also become parameters in your neural network. Number of epochs, number of batches you want to deal with, and so on. And then there are many so-called tricks of the trade. So dropout is one of these. And that introduces a new hyperparameter. So you actually drop some specific results. We have gradient clipping. So in case of exploding gradients, you simply just clip it. You say that, okay, if it's larger than that, I just bring it back to a smaller value. So in general, however, many people actually tend to use what's called batch normalization. There's actually a very good website here, which you can take a look at on neural networks. It collects many of these feature issues here. If you now take a kind of top-down perspective, I'm just going to use 1 or 2 more minutes on it, and then we take a break of 15 minutes. So if you take a top-down perspective on neural networks, is to first divide the training data into 2 or 3 parts. So a typical one is a training set and a validation set, and then a final test set. So we've been mainly splitting the data into training and test. You would often use a validation set where you actually find the final best optimal parameters. And then when you've done that with that, you apply your best model on a test set. So it's a kind of crucial sin to not have a test set. You can read through many of these things, but I wanted to give you kind of limitations of supervised learning with deep networks. So like all these kind of statistical learning methods, when we deal with what we call supervised learning, there are limitations, and we have to keep this in mind. So in particular, neural networks, they are data greedy, and they also need labeled data. This is something which many people forget. So you will be shocked to learn that many of the typical classification algorithms, which use huge data sets of images, many of these images have actually been labeled by underpaid workers. So there's not much machine learning to the part which is essential in neural network calculations for image recognition. So you need labeled data, and that's really the expensive part. So when Amazon and Google and so on claim they have this fancy artificial intelligence / machine learning algorithm which recognizes faces and so on, they've actually been inputting to the training millions and millions of images which have been hand labeled by underpaid workers, humans like you and me. So the supervised neural networks are extremely data intensive. So they are data hungry. And we will see when we move on to convolutional neural networks that we actually want to reduce the dimensionality of the problem, because keep in mind now that when you feed in your inputs, you have a dense matrix, and you multiply that with another matrix or a vector when you transfer the data to the hidden layer, and then you transfer to the next hidden layer, and so on and so on. So you have matrix multiplications with really dense matrices and dense vectors. and they are extremely data intensive. The neural networks actually deal with homogeneous data. So they are not very good at handling heterogeneous data sets or mixed data types. So this is clearly one of the limitations. And many problems are not about prediction only. So in natural science, we're often interested in learning something about the underlying distribution that generates the data. And in that case, it's often difficult to cast these ideas in a supervised learning setting. So while these problems are pretty related, it is possible to make good predictions with the wrong model. And the model might or might not be useful for understanding the underlying science. So which model fits best? That's actually a deep philosophical problem to which you have to apply your insights from your specific disciplines. So some of the remarks which you see here, they apply to neural networks, but others are shared by all kinds of supervised learning methods. And now it's time to take a break. I went a little bit over time, and please excuse me for that. We are going to stop or to pause the recording. Now, in the previous lecture, we discussed some pros and cons of neural networks. Now, one of the things which is very important when we think of neural networks is the universal approximation theorem, which is a very powerful theorem. And this leads to many interesting applications of neural networks. And one of the areas which has attracted a lot of interest in the last years is actually the solution of ordinary partial differential equations. So what I wanted to give you here is a kind of a bird's view on the basic elements. And in order to do so, we also need to remind ourselves a little bit about the basics of ordinary differential equations and partial differential equations. So I'm going to try to catch many birds with just one stone today. And we are going to first look at ordinary differential equations, because then if you've seen the basics here, you know how to transfer this to partial differential equations. And in the lecture notes here, you will also find a kind of a more self-contained material on how we solve differential equations using the standard finite difference methods. So the lecture notes here, they do not cover more advanced methods like the finite element methods. One of the things, just to stay at this overarching level, one of the things you will see is that when we deal with, let's say, one-dimensional or two-dimensional problems, the standard methods are in general superior to the solution with a neural network. So they tend to give a much better result when it comes to the accuracy compared with cases where you have analytical solutions. However, when you move into higher dimensional problems with many different degrees of freedom, neural networks tend to outperform when it comes to both the number of CPU cycles, but also the accuracy you get with respect to a specific ordinary or partial differential equation. So the just to stay again at this kind of higher level, one of the algorithms which you will find extremely useful is automatic differentiation, which we discussed a little bit in connection with the calculations of gradients. So you will see repeated implementations of autograd in the examples which follow now. And this is something which allows us to compute the derivatives of the cost function in a very easy way without going through the hassle of setting up either Taylor expansions in order to find the derivatives, or to calculate derivatives manually and then plug them into the code. So automatic differentiation is one of these extremely powerful algorithms which allows us to solve differential equations in very efficient ways. There are also some textbooks which you may find interesting. And one of these is a textbook which you can download for free, which is a Springer textbook, and it's called An Introduction to Neural Network Methods for Differential Equations. So the material you will see here is actually not that different from what you find in that textbook, except that they also go into more advanced methods. Now, this topic which we are going through now is something which could define, if you are interested, one of the possible paths for project number 2. And I'm going to put that online pretty soon. So you can, if you want to get started with project number 2, you could try to implement differential equation solvers with the neural networks and then compare these to standard approximations. So if we now wish to set up things here, let's go back to the whiteboard and remind ourselves quickly about the solution of differential equations first. So we're going to take differential equations first, and next week we will dive into partial differential equations and remind you of some of the central methods which are used to solve partial differential equations, and then look at the solution of the same equations using neural networks. So the slides which you see here, they were actually, most of the material was actually developed by Christina Hein, who is now a PhD student at the Department for Informatics. And she did an amazing job with this. Actually, she wrote a master thesis on solving differential equations with machine learning methods and standard methods. So let's switch back to the whiteboard and remind ourselves a little bit about some of the things which many of you may have seen before. So this is about solving ordinary differential equations and partial differential equations numerically. Now, if we look at a standard first order ordinary differential equations, so let's just remind ourselves of that. So we have a first order. I hope you don't get offended if we just go back to things which you have seen before in undergraduate classes in either mathematics or computational physics or computational science. So the typical equation which we end up dealing with is something which we would write out as a dy dt. To give an example, where t is and y are the variables. And this could now be given by some function which depends on y. It may depend on the derivative of y, and then it depends on time. It may also depend on higher derivatives, but let's leave that a little bit unspecified. And y and t are then defined in a specific domain. Now, one of the most famous methods, which probably all of you have encountered, is when we discretize. This typically ends up in terms of the simplest possible method, which is called Euler's method, which is given by the truncation of a Taylor expansion. But let's try just to rewrite this equation here, and we can rewrite that in terms of a dy dt minus this f of y of derivative of t equal to 0. And this is normally rewritten in terms of a function f, which now contains simply y, dy dt. It may contain higher derivatives, so just let's include that in order to be more complete. It can have even higher derivatives, but let's just stop at the second derivative. And this is the function which we now want to put to be equal to 0. So a first order differential equation or second order differential equation, suppose we have a second order differential equation. Let's rewrite that one. And these are equations which can be linear or non-linear in the variable y. So we haven't specified that, so just let's leave that open. So a typical second order differential equation is something like this. So it could now be a new function which depends on y prime. Let's assume that this function depends only on the first derivative. And in this particular case, what we often do then is to rewrite it in terms of two coupled first order differential equations, because they are often easier to solve. So this typical stage here is to rewrite in terms of two coupled or more coupled, if you have more variables, obviously, two coupled first order ODEs. So in this typical case, what we would have then would be something which we now could call the, let's define a new variable. And let's call this variable for a variable A, which depends on y or y prime of t. And that's given by a d y dt. So this variable here is now a variable which can be defined if we now define a new variable, which I call y, or y prime of t, which is equal to dy dt. Then I can rewrite everything in terms of two coupled differential equations. And now let me just skip this dependence on y and y prime and t. This would just be given by the derivative of dv or dt. And then I would have a new equation where this v is given by the derivative of dy dt. So this would now give us two coupled first order differential equations, which we then can solve simultaneously. So the typical way we now solve this equation is obviously to discretize. And when we discretize now, we would have a domain of variable, which we have to define. So we would have a y of I, which is in a specific domain. We would have a t, which now goes from a initial time to a final time. So we could call this a t final. We could then define a time step, a delta t, which is given by t final divided by n, where n is now the number of integration points. So that means that we would now have a t, which goes over to a t of I, where this t of I can now be equal. So we could now make this a little bit more general, and we could call this for t0 or t initial. And this is given by a t0 plus a variable I times this delta t. And where this I now runs from 0, 1, 2, up to a discretized value of n. So we have in total n plus 1 variables here. This means also that a variable like y will be discretized, so y of I. And this is also going to be a function which now depends from I equals 0, 1, 2, up to a final n. Similarly, when we look at these other functions, we would discretize them as well. So a goes over to a of I, and this variable v goes over to v of I. And then the next thing which we would do is to actually make a Taylor expansion of these different quantities. So we are now interested in solving the following equations. So we have this equation which we want to solve, and for this quantity a, and then we want to find the equation for v in terms of dy dt. And then when we have v, we actually are going to find the solution for y. So we could assume now that one of these quantities is known. So typically what we would have, if we now go back to the equations which we have here, is that this quantity here is something which is given by a specific function which is known. And then the standard way we would deal with this is to make a Taylor expansion. And if we now look at the variables which we have, suppose now we look at the v. So this v at a time t plus delta t, we can have a t plus minus. This is given by v at a time t plus a delta t plus minus divided by 1 factorial. And this is multiplied with f, or in our case, we actually define this, or let's just rewrite it. So this function here is now given by v derivative. The first derivative, we get a plus a delta t squared divided by 2 factorial. And then we have the second derivative. And then we have the higher order terms of O of delta t cubed. And similarly, we would have y, which is the other quantity we want to integrate up, of t plus minus delta t, which is now equal to a y of t. It's basically the same here, delta t, y prime of t, plus a delta t squared divided by 2 factorial, and then a y second derivative plus an o of delta t cubed. Now you can now, depending on the precision which you want to have, so because you make a truncation in terms of delta t, you can now leave this at delta t squared, or you can just stop at the level of delta t and assume now that the higher order terms are negligible. Often you don't know that. But what you would do now when you discretize these equations, you would get the following: discretize and leave out terms which go with powers of delta t squared. Then we recover Euler's method. So this would simply lead to Euler's method here. And then, as you know, and I'm just bringing this up now because I know that you guys have seen this before, and I hope you don't get offended if I do this reminder of some of the basic ingredients in solving differential equations. You know that you can improve upon this by using midpoint rules, the Euler chroma. You can, for those of you who are familiar with molecular dynamics calculations, you can get an algorithm where you integrate up position and velocities in terms of a correction which runs like delta t squared. That leads to a class of methods which are called the velocity Valais methods. You have the whole family of Runge-Kutta methods and so on. And these are all different methods which are widely used in solutions of ordinary differential equations. So in our case here, we are mainly interested in the solution of differential equations with neural networks. And in order to illustrate the application of neural networks, we are now simply going to compare these calculations with the simplest possible standard finite difference method. So these methods are called finite difference. So it means that what we do now is that we let this t plus minus delta t, we let that one be represented by a y of I plus minus 1. So we make one step to the left and one to the right. This means that we can rewrite these equations as a I plus 1. Since we were looking at one step forward, let's focus on that one. And that's going to give us the so-called forward Euler method. So I'm not putting in an approximation sign, but I'm truncating this at the order of delta t squared. So I'm going to get an algorithm which is now delta t times y of I derivative. Now, in our case, this y of I derivative is given by this equation which we put up here. So let me just bring it back again. So the derivative of the function which we're looking at, y, is given by this quantity v, which is our velocity, which we want to integrate. And in our next case, what we have is that the derivative of the other variable is given by this quantity a. So this quantity a is also something which we assume can be known. This is often the typical case because when we split the equation here, what we did now was to write the second order differential equation in terms of a function which we assume is known. So let's just frame that in. So it's often that we have a known equation for that. And that means that we can plug that one into the equations for the differential equations. So what we would get then would be something like this, and this would again be equal to y of I plus delta t times v of I. And then we would have to solve simultaneously the equation for v, which would then be equal to v of I plus a delta t times v of I derivative. So this is the derivative at the time step t of I. And this is actually, if we look at this one, this is the same as y as a function of t of I plus delta t. And we put a plus minus here. And this function is known, the v of I derivative, because that's given by this function which we call a of I, and which we now can bring back because we have this discretized function which we call for g here. So in most cases, this v and y, which are the quantities we want to integrate up, they are unknown. And the only quantity which is known then is this function g of I, which is the given by the second derivative. And clearly, we also know the time step because we have discretized it. And we have defined a finite difference time step algorithm, which is pretty simple to set up. We specify the number of steps which we need, or the number of variables, n. And then with that one, we can then define the value for this delta t. And then we have an algorithm for setting up the discrete time steps, if we want to call it time. This doesn't need to be time. Then when we have this, we can then discretize the equations. And this equation here is simply called, this set of equation here is just called the forward Euler equations. This gives what we normally call an explicit scheme, which means that the new values are defined explicitly by the previous values. So if I were to take the step backward, so I mean, I take the algorithm in terms of a t minus delta t, then we get something which is called the backward going Euler method, and that leads an implicit scheme. And there's a lot of debate about implicit and explicit schemes when we solve differential equations. And implicit schemes are schemes which will normally give you a solution irrespective of your choice of delta t. When you implement an explicit scheme, you can often run into problems with unstable solutions for a given value of delta t. Now, the value of delta t, even if you can find a stable solution using the implicit scheme, the error you're making is obviously given by the type of truncation which you're doing. So if you truncate a delta t cubed, it means that you will carry with you a mathematical truncation error which goes like delta t cubed. And it means that this will be proportional with higher derivatives, in this particular case, third order derivatives of the function you're looking after. So depending on the type of functions, you can get good approximations with low order derivatives, or you may have to include high order derivatives. You don't know that a priori. So this kind of forward Euler scheme is something which then leads to a set of equations which are pretty easy to solve. And we are going to compare the calculations of neural networks with that. We will stay with the calculations of simpler functions just to demonstrate the applicability of neural networks. So what we will do now is to go back to the equation which you see here, the one which we put up in the beginning. So what we said is that we are going to look at an equation of this type. And let's now stay with a first order differential equation. So what we want to do is actually to minimize this problem here. So we have a function which we want to be equal to 0. And what we could do now is to make an ansatz for the guess of what we're going to look after. So let's try to bring in the concept of neural networks and how we actually are going to solve neural networks for how to solve differential equations using neural networks. So we have discretized the domain. So we have a discretized domain. This means that we are looking now, and we are going to stay with a first order differential equation, order ODE. So let's just stick with that one. And the examples which we're going to look at first are actually first order differential equations. So we have a discretized domain for the variables y. So this is going to be a y0, y1 up to yn. We have similar discretized variable for t. So we have a t0, t1 up to a t of n. We may also have the derivatives of the function. And if we are dealing with partial differential equations, we would have to look at gradients. But now we are just staying with a one-dimensional, the first order differential equation, just to keep it as simple as possible. So we would now have a derivative of y, which again would be a y0, a y1, etc., up to y of n prime. This means that this function which we put up now, this dy dt, which was equal by an f of y prime of t, we rewrote that one in terms of dy dt minus f of y prime of t, and we call this a function f, which we want to be equal to 0. And then what we have then is a discretized version. Where we now simply want to have f of y of I, y prime of I, of t of I equal to 0. And we are now going to try to find parameters from a neural network which actually give us this function. So we are going to now compute the right-hand side and the left-hand side of a differential equation, and we're going to take the difference between the left-hand side and the right-hand side, and this is going to define our cost function. And this is the one we want now to optimize using a neural network. So we are going to now make an ansatz for the solution y using a neural network. So we are going to construct a trial solution. And we are going to call this trial solution a y of t. And this is going to be a function of t here. So I'm not discretizing it yet. And this is going to contain a function which we now are going to define the initial conditions. So we are going to set up a function here, which I'm simply going to call for an h1. And this is going to be a function of t. So this specific function which you see here, that satisfies the initial conditions. And when we move on to partial differential equations, this is also going to satisfy boundary conditions. So keep in mind now that when you're dealing with an ordinary differential equations, we normally don't deal with boundary conditions. We are just interested in initial conditions. So if you look back at the equations which we discretized here for the position y, and this could be the velocity if we want to, or just the derivative of y, then we would normally initialize this solver by having some initial conditions. So in both cases, we would then have a y0 and v0, which are the initial conditions, and they are known. So we specify the initial conditions. And then with initial conditions, we can start solving the problem. And then setting up Euler's method, for instance, is pretty trivial. So what we want to do now is to make a function which satisfies the initial conditions. And then we are going to add a new function, which can be pretty generic. So this function here is going to be a function I'm going to call for h2. And this will depend on this variable t. But then what it is going to include here now is a neural network. So this n here stands now for a neural network, which depends on this variable t, but then it has some parameters theta. And these are the parameters of the neural network. So this function here now is our neural network. which depends on the input t. So t is going to be the input to the network, depends on t as input, or x if you prefer that. And it has parameters theta, which we want to optimize, and parameters theta. To be optimized. So what you see now is that we are going to have a recipe where our cost function is going to be defined by this function f, which you see here, and where we start the calculations with a neural network and a trial function, which then is fed in. So this is our first guess. So that means that if we set up the neural network now, our cost or loss function is going to depends on this function f, which is given by the difference between the left-hand side and the right-hand side. So I need a derivative of the dy, which depends on dy dt minus this other part, which is given by the function f, which is normally a known function, minus this f of y prime of t. And since we are discretizing, so this is going to be our cost function, which is going to be a function of y prime of t. But since we now are replacing y with y of t, it means that our function which we have, so the cost function which we want to optimize, is now going to be a function of this trial function y and its derivative eventually. And it's going to contain t, but it would also contain these parameters theta, which are the parameters which in our specific case are going to be the weights and the biases of a neural network. Weights plus biases of neural networks. So this means that what we have is an ansatz for the solution where we have one term which satisfies the initial conditions. And since we want this one to satisfy the initial conditions, it has no adjustable parameters. Then the adjustable parameters, which are going to give us the flexibility, which allows us to solve the differential equations, they are going to be the weights and the biases of a neural network. And what comes now is actually just a repeat of everything else we have seen till now. So when we have this trial function, where we have a function which respects the initial conditions, and later when we do differential equations, it's going to include the boundary conditions as well. And then we have an additional function h2, which is what our neural networks gives us. And when we now start the calculations, what we will start with is this first guess for this y of t, and this function h2 could then even be set to 0 or just the initial values of a neural network. And then we calculate the derivatives of that function. So it means actually we need to be able to calculate derivatives. And this is where automatic differentiation comes in. And when we now are calculating derivatives, we need to set up the neural networks in order to find the optimal parameters which drive the difference between the left-hand side and the right-hand side in the differential equations to 0. So this is in a nutshell, and from an overarching point of view, the way we are going to solve differential equations with neural networks. So what I was thinking of doing now is, but I see that we are getting close to the hour, is to actually set up some simple examples. So if you now go back to the lecture notes which we have and look at the slides, you will now see a simple example on how you can set up your first ordinary differential equation solver using neural networks. So I'm just going to bring up the slides again so you can take a quick look at it. So as we've said now, any differential equation is an equation which involves having one variable. And in general, the differential equation has something like this. So I just call this f in my notebooks for the uppercase f. And it's going to have a variable x. It could be x or t. This depends on the type of problem you have. And then it has some functionality here, g of x, the first derivative, second derivative, and so on. So these are higher derivatives. So in our case, we just stopped at the first derivative, but you could actually have higher derivatives. So this is your problem. And then, as we said, now you can set up a trial function. You have this function h1, and you have this function h2. And this h1 is a function which makes it satisfy a given set of conditions, whereas n is now our neural network, where you have these parameters, weights and biases included in this parameter p here. And then this h2 then simply represents our neural network. And what we are going to do next week is actually to go through some simple examples. So if we now go through some of these equations here, the first simple case we're going to look at is an exponential decay. And I hope you don't get offended if we just start with some of the simpler cases. In this case, we have a analytical solution, which is simply given by some constant g0 times the exponential of minus gamma times x. So this is going to be the first simple example we will build. And we are going to set up neural networks. You can do that by writing your own code. And in the notes which follow here, you can see how you can actually do this yourself. Alternatively, you can use software like TensorFlow and start setting up your own differential equations. So we are now at the hour. So I'm going to stop here today. And next week, we will spend some time looking at different examples of solving differential equations using neural networks, where we can use our own code. We can bring in automatic differentiation, because this becomes a very useful tool when our functions become more complicated. And in essence, what you will see is that for these simpler cases, neural networks produce good results, but they cannot compete with the traditional methods. But in a nutshell, what you have is that your cost function is defined now by the difference between the left-hand side and the right-hand side of your differential equation. You replace your ansatz for the function with a part which contains the initial conditions and a function which now gives you the flexibility to adjust the parameters, so that your left-hand side minus the right-hand side of the differential equation becomes 0 after a certain number of iterations on your neural network.